Hello everyone, my name is Tian Mao-Zhang. It's a great honor to have the opportunity to present in this meeting. The title of my report is Formulation of Microemulsion Flooding for Post-Polymer Enhanced Oil Recovery. First, I would give you the background of my report. Polymer flooding is one of the most widely used oil recovery methods over the past decades. Use of polymer flooding can boost oil recovery to an average of 50%. However, there are still a large number of oil remains in the reservoir. To further improve the oil recovery for such field, many methods have been proposed, including thermal flooding, gas flooding, micellar flooding. However, each has its own problems. Among all these methods, microemulsion flooding is one of the most widely used methods for post-polymer flooding. The microemulsion flooding combines the advantage of alkaline-surfactant-polymer and such as lower the interfacial tension, reduce the surfactant absorption, and increase the viscosity of the injected flux. However, current use of the microemulsion flooding has the following issues. First of all, study on microemulsion flooding means focused on water-flooded reservoirs, and studies are rarely carried out to address the effect of oil reactivity on the physical behavior. What's more, it has been controversial whether the negative salinity gradient is optimal salinity profile. To solve this problem, the following work carried out. We will study the potential of microemulsion flooding as a post-polymer enhanced oil recovery process and investigate the effect of oil recovery on salinity profile and physical behavior transition. Finally, compare different salinity gradient applied in co-flooding experiment and determine the optimal salinity gradient. Before introducing the research details, I would give you some background about the microemulsion flooding. There are generally three types of microemulsion based on the salinity. Type 3 microemulsion can form at the intermediate salinity range, which has oil on the top, water on the bottom, and microemulsion in the middle. The salinity and type 3 microemulsion and solubilize the same amount of oil and water is called optimal salinity. The salinity profile is also one of the important terms in microemulsion flooding, which means the salinity applied in the pre-flush, chemical slug, and the following polymer drive are in a certain order. The negative salinity gradient is generally considered to be an effective method for improving the efficiency of surfactant. Two types of oil with different total acid number was used for this study. The non-reactive oil was from Dutch oil field, and the reactive oil was from cane oil field with higher acid number. Coreflood test was conducted to investigate the influence of oil reactivity and the salinity profile on the oil recovery. Similar sandstone cones with an average permeability of 1000 millidasy was used. Solubility evaluation was carried out first. As can be seen in the figure, the solutions are uniform and nearly transparent. Even rivers stored in at the reservoir temperature for 7 days, indicating high stability of the formulation. To estimate the effect of oil concentration on optimal salinity, phase behavior test was carried out next. This is the phase behavior for non-reactive oil. It can be seen that type 3 microemulsion was formed at a sodium carbonate concentration range between 1.2% and 1.35%. The optimal salinity was at 1.25% and barely changed with water-oil ratio. This is the solubilization ratio and the interfacial tension calculated from phase behavior for non-reactive oil, and is shown in the left figure. Oil solubilization ratio reached 40, and the calculated interfacial tension are both in the ultra-low level, which is essential to reduce oil saturation. Similarly, phase behavior tests were performed for reactive oil. It can be noted that water-oil for at water-oil ratio of 5 to 5, the type 3 microemulsion formed at a sodium carbonate concentration from 0.8% to 1.1%. However, at a water-oil ratio of 6:4, the type 3 microemulsion formed at a sodium carbonate concentration from 1% to 1.3%, and the optimal salinity rise from 1% to 1.1% when water-oil ratio increased from 5:5 to 6:4. This is the solubilization ratio and the interfacial tension calculated from the physical behavior for reactive oil. The oil solubilization is as high as 60, which is much higher than that of non-reactive oil, and calculated interfacial tensions are also greatly lower than that of the non-reactive oil. The activity diagram is obtained according to the physical behavior result, and ensuring a remarkable difference occurred between these two diagrams. For non-reactive oil on the left, the optimal salinity remains the same. By contrast, the optimal salinity for the reactive oil increased from 1% to 1.5%, and oil concentration decreased from 50% to 10%. Such change in optimal salinity can also be owing to the soap generated by the reaction between alkaline and the crude oil. To further investigate the influence of salinity profile on oil recovery, different salinity gradient was schemed and shown in this table. Salinity profile including constant salinity, negative salinity, and over-optimal salinity was studied. All the Coreflood recovery results for both non-reactive oil and reactive oil are presented in this table, and is shown with the different salinity profile applied. The recovery rates for the microemulsion are apparently different. The highest recovery can always obtain in a manner of negative salinity gradient. However, for the reactive oil, high recovery could also be achieved in a manner of optimal salinity gradient. This is the Coreflood performance of number 2 with negative salinity gradient. The polymer flooding had recovery about 58%, and the reservoir flooding recovers additional 38% over the polymer flooding. The total recovery at the end of the flooding reaches 96%. The surfactant concentration in effluent was shown in the right figure. A low peak with surfactant concentration of 300 ppm was found. The low absorption of high recovery can be explained by the surfactant accumulation on the negative salinity gradient environment that resulted in a long period of type 3 microemulsion. In summary, microemulsion flooding with appropriate salinity profile could recover 90 residual oil left by polymer flooding, and optimal salinity is closely related to water-oil ratio for reactive oil. Therefore, salinity profile for the injected slug should be designed integrate with the oil reactivity. What's more, the use of negative salinity gradient achieved the highest increment oil recovery for both types of oils compared to other salinity gradient. That's all. Thank you.